How do controlled phase gates work in quantum Fourier transform? Imagine you're trying to turn a simple melody into a complex harmony. In quantum computing, controlled phase gates are like the tools that help craft that harmony in a quantum state. These gates are essential for the quantum Fourier transform, a process that changes a quantum state from one domain to another, like converting a sound wave into its frequency. Controlled phase gates involve two qubits, one called the control and the other the target. Think of the control qubit as a switch that decides whether the phase shift happens. When the control qubit is in the state called 1, the gate applies a phase rotation to the target qubit. If the control is in the 0 state, nothing changes. This phase rotation is represented mathematically by a complex exponential factor, which adds a tiny twist to the target qubit's wave. In the context of the quantum Fourier transform, these gates are used to create specific phase shifts between qubits. The amount of phase shift depends on how far apart the control and target qubits are in the sequence. For example, if they are close, the phase shift is larger, like a quick musical node. If they are farther apart, the shift is smaller, like a gentle echo. These shifts are calculated as angles, usually expressed as a fraction of 2 pi, such as 2 pi divided by 2 to the power of a certain number. During a quantum Fourier transform circuit, you start with a series of Hadamard gates that put qubits into superpositions. Then, controlled phase gates are applied to entangle the qubits further by adjusting their phases based on the states of other qubits. This process creates interference patterns that are key to transforming the quantum state into its frequency form. On real quantum hardware, controlled phase gates are designed to be simple and reliable. They are often built from basic gates like controlled NOT gates and single qubit rotations. The precision of these phase shifts is very important because even tiny errors can affect the accuracy of the entire Fourier transform. In summary, controlled phase gates work by conditionally applying phase shifts to target qubits depending on the state of control qubits. These phase shifts build the complex interference patterns needed for the quantum Fourier transform to convert quantum information into a form that can be used for powerful algorithms like factoring large numbers or finding hidden patterns. They are like the subtle brushstrokes that turn a simple picture into a detailed masterpiece in the world of quantum computing.